In section 6, we're going to talk about electron configurations and orbital diagrams. So to get started, let's define first what those are. Electron configurations are used to describe the distribution of an atom's electrons in all the atomic orbitals. This takes the information we've been learning up to this point so far and applies it. The orbital filling diagrams, or simply just orbital diagrams, builds on top of the electron configuration and are used to show the spin of the electrons within an orbital. If you take a look at the examples below, what's in red are examples of electron configurations, and what's in blue are examples of orbital diagrams. You may be familiar with this from a previous chemistry course, but in this video we'll talk about how we can figure out how to write those. So first of all, let's talk about the energy of orbitals. So far we've been talking about this idea that the further you go from the nucleus, the higher in energy that those electrons are. And that's true. But it's not necessarily always an exact increase, and sometimes there's a little bit of oddity that we have to account for. In atoms with many electrons, which is basically more than just hydrogen, the energy levels depend on the shell, which we knew, but also the subshell, which is the shape. If you take a look at the picture that's shown, we can see that the energy increases as we move up. Right here we have the S shape, the first energy level, S subshell. Then we have the second energy level, S subshell. And then we have the second energy level, P subshell. You notice that even though both of these are in the second energy level, we actually find that the three p orbitals that are here are a little higher in energy than this 1, 2s orbital that's right here. Then it keeps going. The 3s, and then a little bit higher, the 3p, 4s, and then notice it ends up going to 3d before it goes to 4p, and so on and so forth. So there's a little bit of variation in the energy of orbitals. So we're going to talk about that when we go to fill in the electrons. One thing I want to point out from this is, do you notice the 4s, the 4p, the 4d, and the 4f. As long as you're in the same shell, in this case n equals 4, what we have found is that the increase in energy is ranked S is the lowest, then P, then D, and finally F. So for example, the 4s is lower in energy than, let's say, the 4f. But that only works when you're in the same energy level, because obviously there's a little variation when you throw different energy levels in, such as 3D. When you go to fill electrons into an atom, they always have to fill in this particular order. This is one way to look at it. Another way is, you may have seen this diagram. This diagram tells you the orbital filling order as you go through. So you'll fill the 1s orbital first, then you'll fill the 2s, then you'll fill the 2p, followed by the 3s, then the 3p, followed by the 4s, and so on and so forth. To be honest, I don't really like using this. I honestly just like looking at the periodic table and looking at it from that perspective. And so that's what I'm going to teach you. I'm going to teach you how you can write electron configurations and fill the orbital, or fill the atom with electrons, just simply by looking at your periodic table. So make sure you have your periodic table handy as we go through example 14. And remember, you should have the areas marked with the S block, the P block, the D block, and the F block. So let's take a look at aluminum. Aluminum is element 13, which means it has 13 protons, but also it has 13 electrons. Those 13 electrons need to be distributed using an electron configuration. So what we're going to do is we're going to map out where are those 13 electrons distributed within the aluminum atom. So here's what we do. Always start at hydrogen and work your way through the rows until you get to the element that you're asked to solve for. In this case, we're going to get to aluminum, which is right here. And I know that's a little small. Hopefully you have your periodic table in front of you. As we go through, the electron configuration is going to have this general template that we'll just keep repeating. We're going to first ask ourselves, what energy level or shell are we in? Then we're going to ask ourselves, what shape are we in? And finally, we're going to ask ourselves, how many electrons are there? And we'll just keep repeating that over and over again until we get to the element that we're solving for. So let's go and get started. Starting right here with where hydrogen is, what energy level am I in? I'm in energy level 1. Remember, the energy level most of the time corresponds to the row number. What shape are we in? I'm in the S shape. So I'm going to write S. And how many electrons are in this one S? There are 2 electrons, the hydrogen, and then also, remember, the helium. This now brings me down to here. Now I'm in the second energy level because I'm in row 2. But I'm still in the S shape. I just happen to be in the second energy level. How many electrons are in the the 2s? There are 2. It would be these 2, lithium and beryllium. Then I go over here. I'm still in the second energy level, but now I'm in the p subshell because now I'm in the p block. How many electrons are there? Well, I go all the way through, which remember, a p subshell can hold 6 total, or 6 maximum, I should say. This brings us now down here. We're in the third energy level. We're back to the S block. And we go all the way through sodium and magnesium, so 2. And hopefully you're seeing a theme. S subshells, as a reminder, can only hold 2 electrons. Then we come over here. We're in the third energy level still, but now we're in the P subshell. But we're going to stop actually just at this first element because we're at aluminum. So we only go 1 electron in to the P subshell. So if I were to clean this up a little bit, there we go, because we're going to need this for the next example. This would be my electron configuration for aluminum. It would be 1s2, 2s2, 2p6, 3s2, 3p1. A way you can check is make sure all of your electrons add up to the number that you need. Aluminum is 13, so it should be 2 plus 2 is 4, plus 6 is 10, plus 2 and 1 is 13. So I know I did it correctly. Once again, what is this information telling us? It's telling us where the 13 electrons are all distributed. I can take a look at this electron configuration, and I can tell, oh, there's 2 electrons in the first energy level. There's 2 plus 6, there's 8 electrons in the second energy level, distributed among the S and P. And then there's 3 electrons in the third energy level, distributed amongst the S and P. Think of it as like an electron inventory of the atom. Now, aluminum wasn't too bad to write, but you can imagine if we have to start writing elements that are really far down, that's going to be a lot. So there's a trick. We can use shorthand notation. Shorthand notation is allowing us to write, obviously, shorter notations rather than writing out complete electron configurations. What we do is we look at the noble gas that was right before the element that we're going to, and we reference that. So, if I were to go back to this example, aluminum was right here. What was the last noble gas that we passed before we got to aluminum? It was right here. It was neon. Neon's electron configuration is represented right here. So instead of writing 1s2, 2s2, 2p6, I actually could just write neon in brackets. That would represent this configuration here in the brackets here. And then just add on 3s2, 3p1. By the way, I want you to write shorthand from here on out unless told otherwise. So you don't have to ask me. Now, before we move on to bromine, some students always ask, well, what if you asked me to write the electron configuration for neon? Can I just do this? And the answer is yes, that would be the electron configuration for neon. So you're probably hoping I'll ask you a bunch of those questions on the exam. I won't, but that's what you would do. All right, let's go ahead and write the electron configuration for bromine, and we're going to now use shorthand. So, if I isolate where bromine is on the periodic table, it is right here. And like I said, this periodic table is really small. Hopefully you have your own in front of you. What was the last noble gas that we had to pass through before we got to bromine? It was right here, argon. So I'm going to reference argon in brackets, and then I'm just going to add on to it. So after argon, I'm going to start right here. I'm in the 4th energy level. I'm in the S block, and there are 2 electrons. Now remember in a past video when I said the S and the P were equal to the row number, the D was equal to the row number minus 1, and the F was equal to the row number minus 2. That comes into play here. So after we go through these 4s2, we then get to the D block. even though we're in row 4, we're actually not in the 4th energy level. We're actually in the 3rd energy level. So I would write 3D instead of 4D. Nevertheless, I go all the way through, so that's a maximum of 10 electrons. When I get back to the P block, I jump back up to the 4th energy level, because S and P are always equal to the row. And I'll write 4P, and then I'll stop at 5, since bromine is where we're going. Lastly, let's take a look at uranium. Uranium is very far down on the periodic table. In fact, uranium is right here. And just to give you an idea of where uranium is, it's in this row, which remember is sandwiched right in here. Okay? So we need to keep that in mind. All right. Nevertheless, what was the last noble gas that we went through before we got to uranium? If we go back, it looks like it was radon, Rn. Thank goodness for shorthand, right? So now let's build on top of that. Right here, we are in row 7, and S is equal to the row number, so 7s2. Now here's where things get a little funky. Go with me on this one. It'll take a little practice, but you'll be fine. Once you go through 7s2, you actually go one element into the D block before you'll drop down and go to the F block. So we need to account for that D element, right? So we're in the 7th row, but the D block is the row number -1. So it actually is 6D1. But here's the even weirder thing. 6D1 is not actually the next energetic. 6D1 is actually out here. We need to leave a little space, because what we have found is that the next area we go to, which is down here, we're in row 7, but we drop down to the F block, so it's row number -2. So we're in the 5F region. We have actually found that's lower in energy than the 6D. So since we have to fill in order of increasing energy, 5F needs to go next after 7s2. I know, it's weird, but a little bit of practice and it won't be too bad. Nevertheless, we ask ourselves, okay, once we're into 5F, how many do we go over? 1, 2, 3. So 5F3. So to make sure I did it right, just as a quick check, I can take a look at, well, radon is element 86, I believe, yep. So 86 electrons were accounted simply in this bracket. Adding on to that, 2 is 88, plus 3 is 91, plus 1 is 92, and uranium is element 92. So this would be the electron configuration for uranium. We already went through shorthand, but I wanted to remind you, or not remind you, but point out that valence electrons are what end up getting shown when we write this shorthand notation. Valence electrons are defined as the outermost electrons involved in chemical bonding. In other words, they're the electrons that are farthest away from the nucleus. And so, when we're taking a look at an electron configuration, we can determine how many valence electrons there are by simply looking at what is the highest energy level. We'll go back into these examples in just a moment, but I want to at least point that out in the electron configurations that we were doing. Alright, for this last video, let's do 2 more practice problems. Write the shorthand notation for these 2 elements. Go ahead and pause the video, write them out to the best of your ability, and then hit play to resume. Alright, here are the answers. Notice that they both reference xenon. For the first one, notice that it's 5D8. If you wrote 5D1 and then 5D7, you don't need to do that because they're both the same energy level and same subshell. So you can just combine those together to make 5D8. That's just in case you did not do that. So I just wanted to point that out there. All right. We're going to go ahead and stop the video here, and we'll pick up and continue on in the next video.